Welcome to my video lecture based on electric circuit theory, paper code PCE 301. Today's topic is band reject filter. Band reject means a particular band will be rejected and a portion of bands will be rejected here, so it is known as band reject filter. Myself, Munmu Banerjee, Assistant Professor of Electrical Engineering Department, Dr. Sudhir Chandra for Degree Engineering College, and at present this is known as Dr. Sudhir Chandra for Institute of Technology and Sports Complex, and this institute is under CIS Group. In this lecture, we will discuss about band reject filter, and previously we have discussed about different filter circuits, introduced different filters, modern active filter, passive filters, and how the active filter is designed in case of low pass filter, high pass filter, band stop filters. Those things we have discussed in my last lectures. So let us start with band reject filter design. Band reject filter is also known as notch active filter. It may be obtained by parallel connection of high pass section with low pass section. Band reject filters actually obtained by parallel connection of high pass section with low pass section, and the cutoff frequency of high pass section must be greater than that of the low pass section, and the output of high pass and low pass sections are fed to an adder whose output voltage V0 will have the notch filter characteristics. That means our input voltage is Vi here, and low pass filter and high pass filter they have parallel cascading, and then it will be added with the adder and we will get the output voltage. And this is the frequency response of band reject filter. Here a particular band is rejected and other part is accepted. So this is band reject filter frequency response, and it is a block diagram for band reject filter. Now the circuit of band reject filter is shown here. This is the band reject active filter circuit using paralleling connection of high pass and low pass filter. We have cascading high pass and low pass filter here. This is high pass filter part, and our power is low pass filter part, and this is the adder circuit to which it is added. This is the adder circuit, and this is our output voltage. So obviously the gain of the adder is set as unity, so we can write that V0 equals to V dash 0 by R2 plus V0 double dash by R3 into R4. So we are getting the R3 equals to R4, and R1 equals to parallel of R2, R3 and R4. Then we have calculate the output voltage in this form. So if AFL equals to AFH equals to AFA, then at center frequency, resonant frequency will be over FCL into FCH, and gain will be A into FCL to FCL divided by FCL by FCH. So this is the diagram for band reject filter, and this is output voltage, resonant frequency and gain of band pass filter for band reject filter. Secondly, band reject filter may be also obtained by using multiple filter band pass filter circuit with adder. That means we can design the band pass band reject filter in two ways. one way we are connecting high pass filter and low pass filter through an arrow. And secondly, we can obtain by multiple feedback band pass filter circuit with an adder. That is, the nose filter is made by a circuit and subtract the output of a band pass filter from the original signal. So this is our input voltage and it is connected with the multiple feedback band filter, and this is the other circuit, and we are getting the output here. So from here we can calculate V0 by Vi, output voltage by input voltage, and we can see that this is the expression of V0 by Vi. Now, writing this the KCL at equation 1, we can get that V0 dash by R dash plus V0 by RF dash plus Vi by R double dash equals to 0. And we are getting that V0 equals to minus RF dash into V1 dash by R double dash plus V0 dash by R dash. And we are getting that this is the expression. At notch frequency, the output is 0. And ideally, we can write that Ts equals to minus R dash by R double dash. But when the frequency Fn equals to Ts divided by Ts equals to minus AF, where AF is the gain of band pass section. With C1 equals to C2, gain of band pass section becomes AF equals to RF by 2R, where AF equals to RF by 2R, that is equals to R dash by double R dash. So the design equations are all those of band pass section and this one. Now we will design a notch filter, that is band reject filter, having resonant frequency 400 Hz, Q equals to 10, and make the resonant frequency gain AF equals to 2. Here FR equals to 400, Q equals to 10, and AF equals to 2. If C equals to 0.1 microfarad, so R equals to Q divided by 2 pi FR C into AF, that is equals to 10 divided by 2 pi into 400 into 0.1 into 25 minus 6 into 2, that is 19.89 kilo ohm. And RF equals to Q divided by pi FRC, that is 10 divided by pi into 400 into 0.1 into 25 minus 5, that is 79.58 kilo ohm. And R equals to R into A divided by 2Q square minus A, that is 19.89 into 2 into 10 to the power 3 divided by 200 minus 2, that is 202 ohm. If R dash equals to 1 ohm, and that is equals to RF dash, and R double dash equals to R dash by A, that is equals to 500 ohm. So we have designed R double dash thermo So the factor is, here we have calculated the value of RF, RR and R double dash. And application of notch filters. Notch filters are used where unwanted frequencies are to be attenuated while permitting the other signal frequency to pass through. For example, 50 Hz, 60 Hz or 400 Hz frequencies from power lines, ripple format, full-wave rectifier, etc. Now we will take an example. Design an active notch filter to eliminate 120 Hz noise. Take the bandwidth and bandwidth value is 12 Hz. Here FR equals to 120 Hz, bandwidth equals to 12 Hz, P equals to 120 by 12, that is K. Now the gain of the filter in the pass band will be maximum 1. So F equals to 1. Let C1 equals to C2, that is 0.1 microfarad, and the value of R equals to 10 divided by 2 pi FR into C1 into 1, that is A. So RF equals to 2R, that is 265.332 kilo ohm we have got. Then we have calculated RR, then we have got RF and R dash arbitrarily 1 kilo ohm, and R double dash we have got 1 kilo ohm. Thus the filter will pass all frequencies between 0 to 114, 114 Hz and 120 Hz, 26 Hz or more. So this is the band reject filter. In between 114 to 126 frequencies it will reject. Now filter approximation. In earlier section we saw several examples of amplitude response curves for various filter types. This always included an ideal curve with rectangular shape, indicating that the boundary between the pass band and stop band was abrupt, and that the roll of slope was infinitely steep. This type of response would be ideal because it would allow us to completely separate signals at different frequencies from another. Unfortunately, such an amplitude response curve is not physically realizable. We will have to settle for the best approximation that will still meet our requirements for a given application. Deciding on the best approximation involving making a compromise between various properties of the filter transfer function, such as filter order, ultimate roll of rate, attenuation rate, near the cutoff frequency, transient response, ripples, etc. If we can define our filter requirements in terms of these parameters, we will be able to design an acceptable filter using standard designing methods. Now we will come to all-pass filter part. This filter passes all frequency component of the input signal without attenuation and provides some phase shift between the input and output signal. The circuit of an active all-pass filter is with lagging output is shown in this figure. So this is a type of filter which will pass all the frequencies and some input and output phase shifting will be happen. So for this circuit, by KCL applying at node X here, we can write that Vx minus Vi divided by R1 plus Vx minus V0 divided by R1 equals to 0. So from there we can calculate that Vx equals to Vi plus V0 by 2. By KCL at node Y, we can write that Py minus Bi divided by R plus Py divided by 1 by j omega c equals to 0. And Py equals to Pi divided by 1 plus j omega Rc. Also from op-amp property, we know that Vx equals to Vy. So it will be Vi plus V0 divided by 2, and that is equals to Pi divided by 1 plus j omega Rc. So from the calculation we can get the values of V0 by Vi, that is 1 by j omega Rc plus 1 by j omega Rc. Thus the amplitude of the gain, that is V0 by Vy equals to 1, that is V out equals to Vin throughout the entire frequency range. Also the phase shift between the input and output voltage is phi, that is equals to minus 2 tan inverse omega Rc, that is phase shift is function of frequency. So this is the characteristics of all pass filter. By interchanging the position of R and C in the circuit, the output can be made leading the input. So we have discussed about band reject filter and all pass filters. Band reject filter means it will reject a particular portion of frequencies and other frequency part it will accept. That means the acceptance range is high here. And for all pass filters means it will pass all the frequencies, and the differences here, input and output side, the amount of phase shift will be there in between input and output side. That is the basic difference of all pass filter input and output part. Otherwise, if all frequencies are passed, that means there is no difference between input and output. So why we need this kind of filter? Definitely not that. It will create the phase shift between input and output parameter. So definitely this filter is required for some different kinds of applications. So that is the characteristics we can see. This is our input voltage, and the output voltage we are getting, that is shifted part. Okay. So where we need shifting of signals, there we can use all pass filter for shifting this. So that is all about our all pass filter and band reject filters. So this total lecture I have taken from the book of Abhijit Chakraborty, Circuit Theory. You can go through that book. This book is very important and helpful for study purpose. You can go to other books like Surajit Bagchi or the Rajewari books. You can also follow the Circuit Theory. Filter is very important chapter of circuit theory, and it is easy to answer. So definitely I will tell that you must answer for filter, because the question comes to this from this chapter is very simple and easiest one. Some theoretical question like what is band pass filter or what is low pass filter, design the band pass filter or low pass filter. Some mathematical problems which are solved here, like designing a filter, low pass filter, high pass filter, those things are come similarly for exam purpose. So it's very easy to answer those questions, and it will come almost 15 mark questions come from this chapter. So if you can attend this chapter, and it is easy to understand. So I will tell that for good scoring in circuit theory, you must go through this chapter and attend the question related to filter in semester exams also. So this is my last topic related to filter. From my next lecture, we will start with new module, and hope you have listened and enjoyed my lecture throughout. Thank you all for listening my lecture.